Okay, here's a fairly standard sort of question. We're asked to determine the cube roots of a complex number, then sketch them on an organ diagram and identify which the principal root is. So this is going to be a use of de Moivre's theorem or de Moivre's theorem. Now, whenever dealing with complex numbers, we're going to it's always of use to find out whereabouts that complex number lies in the organ plane. So let's just draw a little picture of an organ diagram. This doesn't take too long. So there's the real axis, there's the imaginary axis, and that complex number is 3 along the real and minus 2 down the imaginary, so it's going to be down there. So we've got a magnitude, that length there, and an argument theta. So theta looks like it's a negative acute angle, or it's some angle between 270 and 360. Okay, so let's find the polar form of that complex number. So the magnitude is the square root of 3 squared plus minus 2 squared, which comes out to be square root of 13, or 3.605. The argument is the inverse tan of the imaginary part, which is minus 2, over the real part, which is 3, and if you put that in your calculator, I've worked that out in degrees to be minus 33.69, and that seems about right according to our little diagram. So the polar form is 3.605 minus 33.69. Now, in order to work out the cube root, we need de Moivre's theorem, which says that if we have a complex number in polar form and we want to raise that to the power n, that's the same as raising the magnitude to the power n and multiplying the argument by n. Now in our case, it's a cube root, so that means we're raising to the power of a third. So we can find the cube root of this complex number by 3.605 minus 33.69. The cube root of that will be 3.605 to the third, or the cube root of that, and minus 33.69 times a third, or divided by 3. And that comes out to be 1.533 as the magnitude, and minus 11.23 as the argument. Now that's just one root though, and if we're trying to identify cube roots, we know that there should be 3 of them. So where are the other 3? There's only 1 here. Well, you get the other 2 by considering alternative ways of expressing the argument. So in this case, the argument is expressed as minus 33.69, that angle on the organ diagram. But it could also be expressed as minus 33.69 plus 360 degrees, or plus 2 full revolutions, 720 degrees. So if we did that, we would get 3.605 minus 33.69 plus 360. If we did that and found the cube root of that, then we would end up with exactly the same thing for the magnitude, but the argument would now be, we would have a third of minus 33.69, which is the minus 11.23, but also have a third of 360. So we'd add on 120 degrees onto this argument here. And if we add 120 degrees on, we get 108.77. And similarly, the next root will be minus 33.69 plus 720 plus 2 full revolutions. And if we do that, it will be 1.533 again, because we've got exactly the same magnitude that we'll find the cube root of, but the argument will then be another 120 degrees on that, or 240 degrees on the first thing. So that will give us 228.77. And if we found the next one and added another 120 degrees on, we get back to exactly the same values we had to start with. So the 3 cube roots are this one here. I'll label them A, B and C. Now, the question here didn't specify what sort of angles we could use, so these are three distinct roots. If you needed values between 0 and 360, you would have to rewrite that one as 348.77. Sketching those on an organ diagram. Well, A is minus 11, so that's down there somewhere. I'll just put a little A next to that. B is 1.533 and 108, which is just a little bit beyond 90, so that's up there somewhere. There's B. And the C is 228, which is somewhere in the middle there, like that. So there's A, B and C. They're all separated by 120 degrees, nicely spread out throughout the organ plane. And the principal root is the one which is closest to the positive x-axis. So there's the principal